So here we're going to use some tables that list the Gibbs free energy of formation from the elements to calculate a Gibbs free energy of reaction, and then use it to calculate an equilibrium constant. We're going to take a very simple example. We'll take 1 mole of quartz, react it with 2 moles of water, and we'll get 1 mole of H4SiO4, sometimes known as silicic acid. And just as an aside, sometimes rocks that are rich in silica are referred to as acidic, and rocks that are low in silica are sometimes referred to as basic. And that's because of this idea that silica, rocks that have a lot of silica can react with water and form a stronger acid. We tend not to use those terms, acid or basic, when describing rocks anymore, because whether you actually get an acidic or a basic solution depends on a lot of other things that are in the rocks. But we still can get this kind of component, and we can use the Gibbs free energy of formation from, let's say, Roby et al. 1979. So if you want to follow along, you can look up Roby et al. 1979. There are thermodynamic tables. You can get them for free as a PDF file online. So we're going to use their values. So we're going to use Gibbs free energy of formation for each of these fellows. And the Gibbs free energy of the reaction would be this. It would be the Gibbs free energy of formation of the products, which is H4SiO4, minus the reactants. So the Gibbs free energy of formation of SiO2 minus 2 times, because we have 2 moles here, the Gibbs free energy of formation of water. So here we're going to write the reaction, the Gibbs free energy of reaction, as a sum of the Gibbs free energy of formation. So long as we're consistent and all of these are from the elements, and that's what we're going to use for the values that I'm going to show you in a moment. So long as all these are derived from the same thing, let's say from the elements, then we are good and we can make this kind of comparison. It's referred to as Hess's law. So this fellow here from the tables is about 1,308 kilojoules per mole, and from that we will subtract minus about 856.3 kilojoules per mole, and then minus 2 times about 237.1 kilojoules per mole. Let's take that sum. We'll do it on the next board. We're going to erase all this, and that sum, so the Gibbs free energy of the reaction, this is for pure substances, let's put a knot above that, is 22.574 positive kilojoules per mole. To get that third decimal place, I carried out the decimals in the other calculations, even if I didn't write them down. So now we are going to use this equation, one of the most famous and important equations in all of chemistry. So we're going to extract this KEQ values, and it is equal to minus delta G naught, so we can put a minus sign in front of the value we've obtained, minus 22.574 kilojoules per mole. And we can rearrange this. So the natural log of the equilibrium constant is minus 22.574, and that will all be divided by R and T. What is R? R is the gas constant, and the gas constant is about 8.3144 when you're using joules. Here we have to make a correction. This is in kilojoules per mole. So if we're going to use a value of 8.314, we're going to have to convert this to joules per mole. So we get minus 22,574. That's in joules per mole. That's a 7 right there. And then so we'll use a value of about 8.313 or so. And then multiply, we have to divide this by the temperature. And the temperature that we'll use here, all the values that we obtained were at 298.15 kelvins. This is in units of kelvins also, so we're going to put 298 in for temperature right in there. And when we complete that calculation, we find out that the natural log of the equilibrium constant is about minus 9.106. Now, in a lot of tables you'll see not just the natural log, but instead the base 10 log. So the log of K would be minus 9.106 divided by 2.303. That's a 0 right there. So 2.303 is our conversion to change a natural log into a base 10 log, and that gives us minus 3.95. Let's erase the chalkboard again. So what that means is that if the log of k equals minus 3.95, then we can simply get the equilibrium constant, k, by taking 10 to the minus 3.95. And so that will be the value that we can use to obtain actual concentrations of H4SiO4. By the way, this comes out to about 1.11 times 10 to the minus 4. Well, what is the K? This equilibrium constant, I've dropped off the KEQ, is the concentration of our products, H4SiO4, divided by the concentration of our reactants, SiO2, and then H2O, and we had 2 moles of H2O, we have to raise that to the second power, so it'd be H2O squared. But if we have pure quartz, then that's going to be equal to 1, and that drops out. If we have pure water to start with, it'll still be pretty pure when we're done. That can drop off to 1 as well, and 1 squared is 1, which means that this whole thing is equal to the molality, or the concentration, of H4SiO4. So here we can get the concentration. This would be in units of moles per liter of silicic acid in solution. What if you want grams of H4SiO4 in solution? Then we can erase the chalkboard. So we have 1.11 times 10 to the minus 4. That would be the concentration of the H4SiO4 in moles per liter. So that's H4SiO4 in moles per liter. And then we'd multiply it by the molecular weight. There are 96.11 grams of H4SiO4 per mole of H4SiO4. So the moles will cancel. 1.11 times 10 to the minus 4 times 96.11 will give us about 1.068 times 10 to the minus 2 grams per liter. So if we take quartz, if we have, let's say, a container of quartz, let's erase the chalkboard here, and we'll draw a little cup that is full of water. So let's say we have some water in here, and we take a quartz grain, and we'll just draw a little crystal like that. So if we have a quartz grain sitting at the bottom and we let this whole thing equilibrate, there's not a lot that's going to dissolve off, but a little bit of silica will dissolve off into solution. Well, what will be the concentration of H4SiO4 in this saturated solution? So long as the quartz does not completely dissolve, once it's done reacting, we would say that we have a quartz saturated solution. And the concentration in that saturated solution would be the number we've just given, 1.068 times 10 to the minus 2, and that would be in units of grams per liter. So that's how we can use equilibrium constants and thermodynamic tables to calculate the concentrations of dissolved things. In this very idealized case, we had pure quartz here, and it was being dissolved in pure water. If we add other stuff to the system, then that's going to change that number. But sometimes you can get at least ballpark values, and if you know what else is being dissolved in the system, then you can see how the Chatelier's principle might push around that equation, which we'll look at in another video.